Hello again, everybody. Thank you for joining me in another video, the ninth one on differentiation, in fact, for year 13 of Edexcel's A-level maths course. So we're fairly deep into the differentiation now. We know lots of strategies. So what we're going to have a look at right now today is actually the strategy of looking at the second derivative as a way of determining the nature of turning points. So is a turning point, for example, maximum, minimum, or indeed a point of inflection. And the point of inflection part is a big point of confusion. So I'm going to try and address this today, and I'm going to give a thank you to a colleague of mine, which gave me the idea to explain it in this particular way. So anyway, without further ado, let's now have a look at the warm-up questions. So here they are, there's 4, like they normally are. So press pause now, is my suggestion, then press play when you're ready to see the solutions, and hopefully our answers will agree with each other. Okay, so assuming you've done that and had a go, let's have a look now together at solution to warm-up question 1. So question 1, fx equals x to the power 4, sketch f of x above and label its turning point. I'll explain why I've put this on the warm-up in a moment. You might be wondering why I've included such a relatively straightforward and easy question. So I'm hoping its relevance will become clear as I go through a bit more. So anyway, sketching x to the power 4 is going to look like a quadratic essentially. It's x squared all squared. So it's going to be a U-shaped parabola, touching at 0, 0, going back up again like so, without the wobble, but you know, no one's perfect, I can't draw perfectly. So for b, what's f dashed? So differentiate once, that's going to be 4x cubed. Bring the 4 to the front, drop the power by 1. So f dashed is 4x cubed. The second derivative, if I differentiate again, bring the 3 to the front and multiply it by the 4 gives 12. Drop the power by 1 gives x squared. The second derivative when x is 0 is therefore going to be 12 times 0 squared, which is just 0. And the second derivative when x is minus 1 will be 12 times minus 1 squared. Minus 1 squared is obviously 1, times it by 12 is 12, and similarly for the second derivative when x is positive 1, we have 12 times 1 squared, which again is 12. So for part G, it's asking us to have a look at the answers to E and F, where we take the second derivative either side of the turning point of the minimum. What can we say about the sign of f dashed double dash of x either side of that turning point? Well, there's a minimum at 0, 0. At minus 1, the second derivative was positive 12, and at positive 1, the second derivative again was positive. So it's positive here and positive there, so it's not changed signs. So essentially, the sign of f double dash of x is the same on both sides of this minimum. Question 2, simple calculus. So differentiate this function. So dy by dx goes to 3x squared plus 2. Differentiate again, 3x squared goes to 6x. Question 3 is a throwback to some year 13 stats. We're having a look at correlation this time. So we've got the following table showing the marks attained by 8 students studying English and maths. So student A, this is their coordinate, if you like, for English and maths combined. Student B got these scores, student C, and so on. Calculate the product moment correlation coefficient, PMCC. This is essentially the parameter between 0 and 1, which tells us how strong the correlation is, where 1 is perfectly strong linear correlation. So I'm going to remind you how to do this on the class whiz, well, depending on which version of the class whiz you have at least. If we take it here, on this particular version of the calculator, I'm going to press menu. I'm going to scroll to statistics, because understandably this is statistics based for question. Press equals. Now this time, I don't want one variable. What I'm wanting here is to establish a linear relationship. Option 2, y equals a plus bx, is essentially y equals mx plus c, written differently. So this is what we're going to use to test for correlation. So option 2, then x and y, in any order, as long as we're consistent, can be one for maths and the other one the corresponding score for English. So let's have x as the English scores for now. So typing these in, 25 The next one's 18, 32, 27, 21, oops, mispress, 21, there we go, 35, 28, and 30. Then scrolling back up now. This one, corresponding score for this student who scored 25 in English, they scored 16 in maths. Then we've got 11, next one's 20, then 17, after 17 we've got 15, then 26, 32, and finally 20. Press equals. Now we want to work out some options based on this data we've typed in. So press OPTM for option, and what we want here is option 4 for regression calculation. Regression is essentially telling us the PMCC. So we press number 4, and we want our R number. So PMCC R is 0.6856, or 0.686 if you want to give it to 3 significant figures. I'm going to give it to 4, essentially for A, R equals, oops, so for A, R equals 0.6856. Now you might be wondering why I've highlighted this 0.6215 for part B. Well, I'm highlighting this because you might wonder where I've got this number from, which is a fair question. So, given the critical value of 0.6215, which I'll explain, test at the 5% significance level whether these results for Maths and English show that there is evidence of a positive correlation between the English and Maths marks. State your hypotheses clearly. Well, the critical values for a test for zero correlation are given in tables, and you'll get the tables in your exam, in the formula book. So I'm going to show you how you'd use the formula book to work out what the critical value would be if we're testing at the 5% significance level for a one-tailed test. It's a one-tailed test, by the way, because we're testing if there is evidence of a positive correlation. So we're only testing for the positive way, not the negative. So it's a one-tailed test, 8 students. The table would look something a bit like this. So the level, 0.05, which is 5% significance. The sample size is 8, because there's 8 students. So read off 5% and 8. That's where we get our 0.6215 from. So what we need to do now is to compare the critical value 0.6215 with our observed PMCC. And so what we say now is, well, first of all, we actually need to introduce our hypotheses, of course. So H0, we always assume nothing's happened. So H0, assume no change. So H0 is assuming that there's no correlation, but there's a zero correlation. So H0, we say rho, which is a symbol we use for correlation when we're using hypothesis tests for zero correlation. We assume that's 0. Whereas the alternative hypothesis, H1, is that actually rho is going to be positive. Rho is greater than 0. So what we've got here is actually an R value of 0.6856. So then we just say we've observed R is 0.6856, which is greater than the 0.6215 critical value. So because our observed value is greater, more extreme if you like, than the critical value, it's a greater magnitude, then we reject H0. So therefore, we just say reject H0 and give a brief explanation as to why. Reject H0. In other words, there is evidence of positive correlation between English and Maths results. My pen can't keep up with my mouth. I wish I could type faster. I do apologise. But that's essentially what we need to write down to secure full marks. Just a brief conclusion, that's why we're rejecting H0, is because this R value is more extreme. And that's the upshot of what happens when we reject it. That's the evidence of positive correlation. So, warm-up question 4 is about mechanics. So, let's have a look at this one together, talking it through slowly. We've got a particle of mass 2 kilograms, okay? Next, it's sliding down a rough slope that's angled at 20 degrees to the horizontal. So, what I'm going to suggest we do now is we draw it out with a particle mass 2 kilograms, so its weight's 2g acting vertically downwards. So, sketch it nice and big, starting with something like this. So, next, what we're told is, well, actually, before that, what it's normally best to do, almost always, in fact, is to resolve the weight going parallel and perpendicular to the slope. So if that's 20 degrees, the angle in between the perpendicular to the slope, this line here, and the vertical will also be 20 degrees. And then off by heart, what you need to know really, if you resolve this into a forced triangle, the component going perpendicular to the slope is 2g cos the angle, 2g cos 20 in this case, and the component going parallel, in this case down the slope, is 2g sine of the angle, in this case 2g sine 20. So resolving it, and using the resolved components, rather than this one which I'm then going to grey out, we have this. So I'm just going to grey out the 2g and focus on using the components instead, because these are going to be more useful tools to use. So we need to add a bit more information into this diagram of ours. We're told a force of magnitude P is acting parallel to the slope and is attempting to pull the object up the slope. So this force P is acting in this direction, going upwards. So P is acting like this. However, we're also told about this slope that it's rough. Before I come to that though, there's also going to be a reaction force which is acting perpendicular and away from the slope. So R is acting perpendicular away and is going to be opposite to this 2g cos 20 course. I'm going to mention more about this in just a moment. We're told it's a rough slope, and also about it being rough, we're also told that the coefficient of friction on this slope and between the particle is 0.3. So what we can say here is, because again the particle's sliding down, the friction is going to be at a maximum, and friction always acts to oppose motion. So the friction will be acting up the slope and will be at its maximum. Maximum friction is mu multiplied by the reaction force. Mu is the coefficient of friction, which is 0.3, and R is this R here. So I'm going to label on FL in green, and going one step further, using the FL is mu R, I'm going to call that equals 0.3R, because our mu, our coefficient, is 0.3. The final thing is to note the acceleration. So this particle, it says, is accelerating 0.2 meters per second squared down the slope, which is going in this direction. So we can now get set on actually tackling this. So first of all, what we need to do is apply F equals ma, but we don't know enough forces yet. So first of all, let's focus on the forces acting perpendicular to the slope. So forces acting in this direction. So we've got R going up and away. That must be equal and opposite to 2g cos 20, because there's literally no acceleration going in this direction. So this force here must be equal and opposite to 2g cos 20. So R equals 2g cos 20. Now considering forces going parallel to the slope, up and down, like so, we're now going to apply F equals ma. So over here what I'm doing is F equals ma essentially. So the resultant force will be going down the slope. So it'll be down and positive. So the forces going down parallel to the slope is just this component here, 2g sine 20. The forces or components of forces acting opposite to this direction, going up and parallel to the slope, we minus away because they're acting against this force. So we minus off P, and we can also minus off FL, but we know FL is actually 0.3 multiplied by R. So I can say now that's going to be 0.3 multiplied by R, which we worked out here by resolving perpendicular to the slope. So I'm going to fill in that the R is 2g cos 20. So that's the resultant force. So I'll underline that. That's the overall force going down the slope, and that will be equal to the mass 2 multiplied by the acceleration, which we're told is 0.2. So all this here, apart from p, is just going to be a number. And on the right-hand side, 2 times 0.2 is 0.4. So the red and this green and purple is going to be a number. So we're going to have minus p at the end. So let's just work out what this value is here. So if I just do 2 times g, now g is 9.8. So 2 times 9.8 multiplied by sine 20, close brackets, then minus the 0.3 multiplied by 2, multiplied now by g, so multiplied by 9.8, then multiplied by cosine 20, close brackets. That gives us a value of 1.178, and so on and so on. So 1.178, blah, 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 minus p equals 0.4. So by rearranging this, basically subtracting 0.4 from both sides, then adding p or whatever you want to do, I'm going to see now that p is going to be this 1.178 minus 0.4. So minus 0.4, p must be 0.778 to 3 significant figures. Newtons, really, we should say, because this is in kilograms, acceleration's in meters per second squared. So it's going to come out in SI units. The SI unit of force is the Newton. The main bit of the lesson. So, using second derivatives to test if a curve is concave or convex. So, you can use second derivatives to show whether a curve is concave or convex. Now, as silly as it sounds, concave means they look like caves. And thank you to Mr. Brockway for reminding me of this. I think it's a very silly explanation, but I mean that in the nicest possible way. Silly sticks in my head. So a concave curve looks like a cave. So essentially, imagine a nice cave like so. Then if I have a curve going around the mouth of a cave, like so, concavity, or something which is concave, is basically a downwards smile. It's a frown. It goes there, and it's going downwards. So the gradient is decreasing at all points if it's concave. I'm going to come to the definition formally next. So if a second derivative at any point is less than 0, then the curve is concave on that particular interval of a curve. So to use an example of a curve, here's the curve y equals 5x minus x squared, which is a n-shaped parabola, and obviously it's got a turning point here, which is a maximum. So if we did the second derivative, first of all, the first derivative would be y equals 5 minus 2x, so dy by dx, then differentiate again, d squared y over dx squared, or f dash dash x, in terms of function notation. The 5 vanishes, I just get minus 2. So the second derivative is minus 2. So because of that, because the second derivative is minus 2, what that means is a curve is concave for all x being a real number. So dy by dx is a gradient. The second derivative is the rate of change of that gradient. If it's negative, what this means is the gradient is decreasing. So here, the gradient starts off being really steep, a bit less steep, flat, so 0, a bit less than 0, a negative gradient, take away something else, a more negative gradient. So the gradient starts positive, but is decreasing each time. So the gradient might be 10 here, 8, 6, 0, minus 2, so it's going down at each point. So that's if it's concave. The second derivative is negative. Now, what if a curve is convex? If a curve is convex, the second derivative is greater than 0. Or put it a different way, if a second derivative is greater than 0, the curve is convex. So that's going to be a U-shaped parabola, if it were parabolic. It's basically going to be caved in. Not a cave, but sort of like it's been punched in almost. So if I take this example, y equals e to the x, if I differentiate first to find dy by dx, this function is a special function, it just stays as it is, and same for the second derivative, nothing changes, e to the x. So the second derivative and the first is itself. As you can see here, y is always positive, therefore this second derivative is always positive. So here, dy by d squared y by dx squared, or f dash x, is greater than 0. greater than 0 because it's e to the x. That's always positive. And because it's always positive, you can see that the curve is convex. So, to recap, if a second derivative is negative, it's concave. If a second derivative is positive, then it's convex. However, if the second derivative is 0, we're not so sure. What we need to do then is you need to inspect each side of the point. It might be a maximum, it might be a minimum, or it might be a point of inflection. Now, my mistake, and why I did question 1 of a warm-up, is I often encounter, and I was guilty of this myself as a student, I used to take these examples here, and think if a second derivative is negative, it's concave, if it's positive, convex, then I jump to the conclusion, so if it's 0, it must be a point of inflection. Not necessarily. If a second derivative is 0, then it might well be a point of inflection, but what we need to do is to inspect a bit further. And this is what I'm going to go on to and explain in a bit more detail in just a moment. Looking at this curve here, for example, this cubic, y equals x cubed minus 6x squared minus 9x. So if I take the first derivative, x cubed goes to 3x squared, 6x squared goes to 12x, so that goes minus 12x, and minus 9x differentiates to minus 9. Differentiate again for the second derivative, or f dash dash x in terms of the function notation. 3x squared goes to 6x, minus 12x goes to minus 12, and the constant minus 9 vanishes. So the second derivative is 6x minus 12, so let's think about that and when it's equal to 0. So this one here is going to be equal to 0 when x is equal to 2. So second derivative is 6x minus 12, and that's going to equal 0 when x is going to be equal to 2. When x is less than 2, this is going to be negative. So this red is where the second derivative is negative. And like we said here, if a second derivative is negative, we've got concavity, it's concave. This bit here is concave. When x is bigger than 2, the second derivative will be 6 times something bigger than 2 minus 12, which will be positive. So after 2, the second derivative is then positive, which makes it convex. So in blue is convex. So we can say here that the second derivative is 6x minus 12, so it's concave for when x is equal or less than 2, and convex for when x is greater than 2. So the next bit is quite important, using second derivatives to test if a point is a maximum, a minimum, or a point of inflection. So I'm going to use now a flow chart to make this as clear as I possibly can, and I've basically adapted, dare I say, stole this idea from the very kind Mrs. Able-White that shared this to us all on an email. So thank you very much, Mrs. Able-White. You've inspired me in this particular way, and to pay you back, I've stolen your idea. So thank you very much. Ha ha ha. So using the second derivatives, let's go through this step by step very carefully. A point of confusion for many a student, myself as well at the time. So we've already seen in year 1 of the course that maximum and minimum points can be found by finding where the gradient's 0. And then after that, we can use a second derivative to show if that particular point is a maximum or a minimum. Confusion can often occur, though, with points of inflection. So a point of inflection is where the graph changes from being convex to concave, or vice versa. So the flow diagram, I say below, on the handout it's below, on the video it's going to be on the next sort of screen, is going to detail exhaustively the process for identifying the nature of stationary points for a differentiable function. So to investigate a point where the value of x, the particular value of x is a, for example. Let's think about what we might have. So this notation here means the gradient when x is a. So we're saying here, when x is a, is the gradient when x is a equal to 0? So let's just think about this. There's going to be different options. But let's assume that the answer is yes. If the answer is yes, there's still different things to consider. So, 3 different options. First of all, if it's a yes, then we might have that the second derivative, when x is equal to a, is greater than 0. It might be less than 0, or the second derivative might be exactly equal to 0. So we need to test this next, and that gives us more information. So what if the second derivative when x is a was greater than 0? Well, if that's a yes, that proves it's a local minimum. And that's because if the second derivative is positive, that means the gradient's increasing. That means it's going the right way round. The only way is up, as a just about 90s band, I think it was, or maybe 80s sang. So it's going up, so therefore it's a minimum. However, if the second derivative is negative, then it's going to be a local maximum. That's because if a second derivative is negative, that means the rate of change of the gradient is negative. So the gradient's going down and down and down, it's decreasing. So it might start positive, but it's going downhill. So it's reached the top, and then it had to stop. Sad story. That gives a maximum at the top. Or it might be now that the second derivative was actually equal to 0. Now in this case, it's not necessarily a point of inflection. What we do now is we work out the second derivative and then evaluate that just before a and just after a. Typically I'd say just 1 decimal point, 0.1 before and 0.1 after. And when we do that, we then check the sign of the second derivative either side of a. So, 3 different options. If the second derivative is negative before and after a, we'll have a local maximum. Again, if it's negative, it's going downhill, but that gives a maximum. If the second derivative is positive before and after a, that's a local minimum. Then positive going that way up, but makes a minimum. If, however, the second derivative does change sign, so it changes from a plus to a minus, or from a minus to a plus, that's when you have a point of inflection. So that's something where, for example, it goes from decreasing to then increasing, like so. So it's like the hinge point where it changes from going clockwise to anti-clockwise, or vice versa. So that's if the gradient's equal to 0. So if it's a stationary point, you could have a point of inflection. However, what you might find is a non-stationary point of inflection. So these work, for example, if you're going uphill, for example, something like this, curving up, but going down a bit. Bad example, hold on, I'll just get rid of that. So going up, but about to curve down, then before it can start to curve down, it changes its mind and starts curving back up again, but never actually is quite 0. I'm not the best artist, so I'm not the best at illustrating, but this will make more sense when we come to it. So, like I'm saying, if the gradient isn't 0 when x is a, we still might have a point of inflection. To test if it is or not, what we'd need to do is take the second derivative at a again, much in the same way as we'd take the second derivative if it were a stationary point. So again, what we're going to do now is check the second derivative just before a and just after a. So if the second derivative at a is 0, again it might be a point of inflection. So again, now from this, essentially there's only going to be 2 options. It either is a point of inflection or it's not. It can't be a maximum or minimum because the gradient of this point isn't 0. So if d squared y by dx squared changes sign of a point, then we do have a point of inflection. This one's a non-stationary point of inflection though, because the gradient isn't 0. If d squared y over dx squared doesn't change sign, then it's not a point of inflection. And if the gradient wasn't 0 and the second derivative wasn't 0, then that certainly isn't a point of inflection either. It's nothing at all. It's just a point on the curve which is moving on and isn't stationary. So this might be worth referring to as we tackle some worked examples. Worked example 1. We have f of x is x to the power 4 plus 5x cubed minus 9x squared minus 1. We're asked now to show, using calculus and algebra, that f of x has stationary points when x is 0 and x is a plus or minus b root 57 all over c, where a, b and c are integers to be found. So, part A was a bit of a mouthful, but let's have a look. So we need to find the stationary points. Essentially all this means is we need to differentiate once. So for part A, let's just do f dashed of x. So f dashed of x is going to be 4x cubed plus 15x squared minus 18x. Now, it says use calculus and algebra, so not just bashing on our calculators. So will this factorise or can we do anything with it? Well, we can actually factorise out an x. So we have x, then brackets, 4x squared plus 15x minus 18. So therefore we can say there's going to be stationary points when f dashed x equals 0. So essentially that just means we can set x brackets 4x squared plus 15x minus 18 to be equal to 0. So therefore either x is equal to 0, so that's one solution which we needed to show, or it may be the case this quadratic here is equal to 0. So from here, what we can do is use the formula, quadratic formula. So x is going to be equal to minus b, minus 15, plus or minus the square root of b squared, which is 15 squared, minus 4 times a, which is 4, times c, which is minus 18, all over 2 times a, which is 2 times 4. So we just type this into our calculator. It's a show that question, so we can't just rely too heavily on the class whiz. So if we just do this, so minus 15 plus square root of 15 squared minus 4 multiplied by 4 multiplied by negative 18, all divided by 2 times 4. That gives us a value of minus 15 plus 3 root 57 over 8. So therefore we want to be minus 15 minus 3 root 57 over 8. So our a, b and c are 15, 3 and 8. So therefore or x equals minus 15 plus or minus 3 root 57 all over 8. So those are the two options. So B, B says to find f dashed x. So for B, f dashed of x, we're going to differentiate again. So we can differentiate f dashed of x now. So 4x cubed, 3 comes to the front, times is by 4 to give 12. 1 less than cubed is squared. 15x squared becomes 30x. And then minus 18x goes to minus 18. Then for part C, it says using the answer to B, state in terms of x the intervals on which f dashed of x is convex and on which it's concave. So if a curve is convex or concave is defined upon if the second derivative at those particular points on the curve is more or less than 0. So it's critical about finding where the second derivative is 0. So what we're going to do for part C is set f dashed x equal to 0. So let's set f dashed x, which is 12x squared plus 30x minus 18 equal to 0. Now you can do this on the calculator and get the solutions, that's fine. I'm going to do it the old school way though. This will factorise quite nicely. So if I divide everything by 6 to get it into a simpler form, that's going to be 2x squared plus 5x minus 3 equals 0. So this will factorise now, using whatever method you want, into the plus 5, so it needs to be like so. So factorises into that form. So therefore, the second derivative is equal to 0 when this bracket here gives a solution of a half, and also if this bracket's equal to 0, x would be minus 3. So if now we imagine a graph of the second derivative for a second, the second derivative is this quadratic. It's 12x squared plus 30x minus 18. So if I just imagine a little graph of this second derivative now, then it's equal to 0 when x is a half or minus 3. So imagine the graph of it like now. It's a positive parabola because it's a 12x squared. So that's a graph of f dash dash of x. So we can see where it's positive and see where it's negative relative to these critical points. The critical point is a half, that critical point is negative 3. So at this region here, that's where clearly f dash dash of x is positive. So down this way, we've got that f dash dash x is positive. In between minus 3 and a half, we have that it's negative because underneath the x-axis. And a half or more, we can see that f dash dash of x is positive yet again. So what this means is essentially there's 3 different parts. So using this little sketch, we can now answer part C essentially. So as long as you remember when it's concave and when a curve is convex. So for part C, it's going to be convex. We need to remember a curve is convex, caved in other words, convex is something like this. When the second derivative is positive, that's when it's caved in, when you have a minimum somewhere. So the second derivative is positive when f dashed of x is less than minus 3. So basically, it's convex, x is less than minus 3, or equal to, and also over here when x is a half or greater. And then it's concave in between these 2 points. So it's concave. Now, the examiner won't be too concerned with an overlap of these inequalities, but to make sure there's no overlap, I'm going to make sure that there isn't by using this strictly greater than inequality. So in between the values of minus 3 and positive 1/2, that's when the second derivative is negative, therefore it's going to look sad, therefore like a cave. I'm going to show you now a sketch of the actual function, f of x. So f of x is actually like this. So as you can say, this bit's convex, up to where x is minus 3. Then the blue bits here, concave, where it would have caved downwards. And then at half, it starts curving upwards, when once again, f dash dashed becomes positive. So that's the actual graph, but the answer is convex. I'll move this out of the way so you can see it slightly clearly, a bit more clearly, like so. So it's convex when x is less than or equal to minus 3, or x is half or greater. Concave when x is in between those 2 values. Let's have a look at the second worked example. This time, a curve has equation y equals x squared plus kx plus 13 minus 8 over x minus 5, where k is a constant. Given that the curve has stationary point P, where x equals 3, show that k equals minus 8. Now, before I get into this, I'm going to assume that you might not feel confident of differentiating something like this, where it's not just 8 over x, but it's 8 over x minus 5. So just in the corner, I'm just going to put a little aside, should you wish. So this bit hopefully shouldn't trouble you, but you know, you are human, you may have forgot. So if I just think about here, so if I just call y equals 8, I know it's minus, but just think about this bit here. So y equals 8 over x minus 5, which I'm going to call now 8 u to the minus 1, where u equals x minus 5. Then we can use a chain rule. So dy by dx, dy by du times du by dx. So if u is x minus 5, du by dx is 1, so du is the same as dx. So all we need to do is just differentiate this as though it were an x. So we get minus 8 u to the minus 2, which in terms of this is actually minus 8 over x minus 5 squared. And then if we want the second derivative, we can differentiate this again. d squared y over dx squared. Again, because du is dx, this time we bring that minus 2 to the front. Minus 8 times minus 2 is positive 16. Then u to the minus 3, which in terms of x is 16 over x minus 5 to the power 3. So that's just considering this bit here. So you might have not needed that, but if you did, there's a little refresher of the chain rule for differentiating these types of functions. So show that k equals minus 8. Well, we're told here that the curve has a stationary point where x is 3. Stationary points a curve when the gradient is 0. So let's do dy by dx and set it equal to 0 to find the stationary points. So dy by dx, x squared becomes 2x, kx differentiates to k, the constant 14 disappears, and this one here, this minus 8 over x minus 5, differentiates to this, so it goes to minus 8 u to minus 2, which is this. So it's minus 8 over x minus 5 squared. But to make this read slightly less confusingly, I'm just going to change the minus to a plus. I'm going to say that's going to be equal to 0, of course, at a stationary point. So set it equal to 0. So 2x plus k plus 8 over x minus 5 squared equals 0. And then, so when x is equal to 3. So if I sub in x is equal to 3 into this, so I'm going to get rid now of instance of x and replace them with a 3. Like so. Now we just work out what this is. 2 times 3 is 6. K is just k. This fraction becomes 8. 3 minus 5 on the bottom is minus 2, then minus 2 multiplied by itself, minus 2 squared, minus 2 times minus 2 is positive 4, equals 0. 8 over 4 is 2, so 6 plus k plus 2 equals 0, therefore k equals negative 8. Part B, determine the nature of the stationary point P, given a reason for your answer. Well, what we can do here is take the second derivative. And to take the second derivative, I'm going to use the first derivative, dy by dx. So for part B, let's start with what dy by dx was. So dy by dx, we had 2x plus k. I'm going to write a third term different. I'm going to put it as 8, then x minus 5, all to the minus 2. So if I differentiate this again to get d squared y over dx squared, 2x will go to 2, the constant k will disappear. Differentiate this, the minus 2 will come to the front and times by the 8, so positive 8 times minus 2 is minus 16. And then I drop the power by 1 as well, so it goes to minus 3. So to determine the nature of this point, I can actually check what the value of the second derivative is when x is actually equal to 3. So what's the value of the second derivative at p? So when x is 3, what happens? So we have d squared y over dx squared equals 2 minus 16, 3 minus 5, all to the minus 3. So what's that going to be? Let's just see. 2 minus 16 brackets 3 minus 5 to the power minus 3. That gives us a value of 4, but essentially what matters is it's positive. So in brackets, that's a positive value. So because the second derivative is positive at point P, what happens is the gradient is increasing. So it's going up, 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 up like so. Therefore, it's convex. It's not like a curve, it's not like a cave, rather. It's caved in. So therefore, this is going to be a local minimum. So therefore, for B, we have a local minimum. Finally, part C. Show that the curve has a point of inflection where x equals 7. So for part C. So when x is 7, what we can do here is actually just work out what the second derivative is when x is 7. So when x is 7, the second derivative is going to be 2 minus 16, 3 minus, sorry, that's now going to be 7 minus 5, because now x is 7 to the power minus 3. And if we try that, you should find that it gives 0. So I just alter this and change a 3 to a 7. We get 0. Then what we need to do, because that isn't necessarily a point of inflection, we need to test the second derivative either side of x equals 7. So now we try, for example, when x is 6.9. So when x is 6.9, d squared y over dx squared. Let's just work out the value. So if I just alter the 7 and change it to a 6.9, I get this awkward decimal. So I'll change it to a decimal, sorry. So about minus 0.33. Importantly, that's just a negative value. Now try one decimal place above 7. Let's try when x equals 7.1. That gives d squared y over dx squared equal to, well, let's see. If I change from 6.9 and input 7.1, what we get now is a value of 0.272, about 0.27, but essentially that's positive. So then we can conclude, because there's a change of sign in the second derivative, therefore, where x equals 7, that is a point of inflection. So since f dash dash x changes sign, either side of where x equals 7 and f dash dash of 7 equals 0, then there is, my writing is awful, I do apologise, then there is a point of inflection when x equals 7. Finally, worked example 3. Now we've got a curve C with equation x squared tan y equals 9, where y is between 0 and pi over 2. We need to show that dy by dx is minus 18x over x to the power 4 plus 81, and then afterwards we need to prove that C has a point of inflection where x is the fourth root of 27. So here's where we need to use our skills we've built up from chapter 9 so far. So what we need to do here, differentiate both sides. So, for the first bit, x squared tan y is actually a product. So if we differentiate x squared tan y, remember, if I differentiate a product, let's say u v dash, I differentiate the first bit, keep the second the same, then leave the first one as is, differentiate the second. So that's here if you need. So over here, I'm going to differentiate x squared, which gives 2x, leave tan y as it is, and then I'm going to leave the first bit, x squared, as it is, and differentiate tan y. Now, if you differentiate with respect to y tan y, this is implicit differentiation. So we differentiate tan y as if it were tan x. So what would tan x differentiate to? Ideally, you need to remember that tan differentiates to sec squared. You can derive it yourself using the product rule if you want to, but ideally, remember tan differentiates to sec squared. So differentiating tan y, that will go to sec squared of y. Then remember, when we differentiate implicitly, we just stick on the end a dy by dx. And of course, if we differentiate 9, that's a constant, so we get 0. So now if I subtract 2x tan y from both sides, I'll now get x squared sec squared y, lots of dy by dx, equals minus 2x tan y. So I want this to be all in terms of x though. So in a minute, what I want to do is actually work out what this is without being in terms of tan y, but in terms of just x's. So let's just pause for a second and think about this expression here. So from here, if I divide by x squared, I can see that tan y is just 9 over x squared, like so. And we can use this later on. For now though, to get dy by dx on its own, I need to divide both sides by x squared sec squared y. So if I do that, divide by x squared sec squared y, I then can see that dy by dx equals minus 2x tan y all over x squared sec squared y. However, I want this all in terms of x's. So tan y, that's easy enough. I know that tan y now is this, but sec squared is no good to me. Sec squared, I need to remember an identity that we can get sec squared in terms of tan squared. So I remember this identity in a very stupid way. So I remember this identity in terms of, if you take one person and they get a tan, well, indulge me, just call it a tan squared. They may well arrogantly think they look rather sexy with their beach body. So one person plus a tan squared, sec squared. Inappropriate, but if it works, to remember it works. So basically, we can replace a sec squared y with a 1 plus tan squared y. So just rewriting this in terms of x, so dy by dx is going to be minus 2x multiplied by 9 over x squared, because that's what tan y is in terms of x. On the bottom, you're going to have x squared, and then sec squared is 1 plus tan squared. So that's going to be 1 plus 9 over x squared, all squared. So square the top, 9 squared is 81. The denominator, x squared squared, is x to the power 4. This obviously looks quite unwieldy. What I'm going to have on the bottom of this fraction here is going to be a x squared. Now I don't want anything on the bottom of a fraction. So if I multiply both numerator and denominator by x squared, I'll get the required result. So minus 2 times 9 is 18. X divided by x squared is 1 over x, but if I times by x squared, that will give us a minus 18x. On the bottom, x squared times x squared, x to the 4 times 1 is x to the 4. X squared times x squared, x to the 4, multiplied out by 81 over x to the 4, gives us the plus 81 as we needed. So it's shown that dy by dx is that. So we now need to prove that there's a point of inflection when x is the fourth root of 27. Now there's a point of inflection when the second derivative is equal to 0. So what we need to do here is to actually work out the second derivative. So for now, if I just imagine this is y, so I know it's not, but let y equals minus 18x over x to the power 4 plus 81. then to differentiate that, dy by dx, second derivative, would be, basically this is the quotient rule. So what I need to do here is I differentiate the top of the function, so get minus 18, multiply that by the bottom of the bottom, then I minus the bottom function differentiated, so this differentiates to 4x cubed, that multiplied by the numerator, so that times by minus 18x, all of that's going to be over this bottom function squared, so x to the power 4 plus 81 squared. So at the second derivative, basically this is the second derivative because differentiated that again. So in other words, therefore what I've done here for the curve, which is this, the second derivative, d squared y over dx squared. So this is just in a little thought bubble almost. So from dy by dx to d squared y over dx squared, I now know it's all this thing here. So I'm going to neaten it all up. So I've got x to the power 4 plus 81 squared. This at the top, minus 18x to the 4, then minus 4 times minus 18 is plus 72. So 72x to the 4 here, minus 18x to the 4, that gives 54 x to the power 4, and the number is going to be minus 18 multiplied by 81. So minus 18 times 81 gives us minus 1,458. So the second derivative is going to be equal to 0 when the numerator is equal to 0. Equal to 0. So then we need to work out what x is. So add 1458 to both sides. 54x to the 4 equals 1458. Divide by 54. So 1458 divide by 54 gives 27. So therefore, finally solving for x, so therefore d squared y over dx squared equals 0 when x equals, if I take the fourth root of both sides here to solve this, the fourth root of that gives me x, and the fourth root of that. So the second derivative is equal to 0 when x is the fourth root of 27. Now the fourth root of 27, we need to work out as a decimal. That's going to be approximately equal to 2.279. And so on and so on. So what we need to do now, this showing the second derivative is equal to 0 isn't sufficient. What I need to show is that it changes sign either side of when it is equal to 0. So let's try when x is 2.27. So d squared y over dx squared. Basically, we can plug into this here if we really want to. So let's try that. So just typing in here. So this becomes 54 x to the 4. And so if we're going for a value of 2.27, we're going to use x as 2.27. So 2.27 to the power 4 minus 1458. All of that divided by, in brackets, our x to the power 4. So 2.27 to the power 4 minus 80, sorry, plus 81 rather. All of that squared. And so at 2.27, we have a value of minus 2.09 times 10 to the minus 3. Minus 2.09 times 10 to the minus 3. And all it really matters is that's a negative value. So at 2.27, it's negative. Let's now just go one decimal point over. So let's try when x is 2.28. Let's see if that alters the sign of the second derivative. So then we get that d squared y over dx squared will be a different value, but of course, what? So all we need to do now is alter our 2.27 to 2.28 and see how that affects the sign, if at all. Knowing that, of course, if a sign is affected, if a sign changes, that confirms it's a point of inflection. This here gives us a positive 1.08 times 10 to the minus 4. Ultimately, that's positive. So now we make our conclusion. So we can say now that because f dash dashed at the point where, what was the point we're actually trying now? Almost forgot, we did so much work. Point of inflection at 4 root 7. So the second derivative at the fourth root of 27 was 0. And just before, f dash dashed of 2.27 was negative, f dash dashed of 2.28 changed sign to positive. Therefore, there's a point of inflection at the point where x is the fourth root of 27. Inflection at the point where x is the fourth root of 27. And so that's done. And those last two examples, by the way, were exam-style examples. So now it's over to you to try some of these on your own. So in the book, if you try question 1, then questions 5 through to question 11 of exercise 9I on page 259, that should give you a good grounding on these questions. So keep plugging away, never give up, seek help if needed, and keep going strong and be kind to yourself. So thank you for listening once again. Stay tuned for the next one, and I hope to see you around soon. So for Mr. Bailey, it's goodbye once again for now.